Let's get right into it. Science. It is the beacon of human progress. It gave us electricity, medicine, the internet, and those little non-stick pans that give you cancer if you scratch them. We like to imagine laboratories as pristine, sterile sanctuaries of logic. We picture men in white coats carefully measuring liquids into beakers, nodding solemnly as they unlock the secrets of the universe. But the reality is often much stupider. Because no matter how much math you know, or how many degrees hang on your wall, you are still just a hairless ape with anxiety, capable of making colossal mistakes. And when you make a mistake in a kitchen, you burn your toast. When you make a mistake in a high-level physics lab, you unmake your own DNA. Let's go back to 1946. The war's over, but the toys are still lying around. We are in Los Alamos, New Mexico, the birthplace of the atomic bomb. Meet Louis Slotin. Louis is a brilliant physicist, but he has a bit of a reputation. He is what you might call a cowboy scientist. This sounds cool, like Indiana Jones but with radiation poisoning, until you realize that safety regulations exist for a reason. Slotin is famous for performing an experiment called tickling the dragon's tail. It involves taking a 2-kilogram sphere of plutonium, let's call it the core, and bringing it to the very edge of criticality. That means making it almost explode, but not quite. To do this, he uses 2 half-spheres of beryllium. When these 2 halves close around the plutonium core like a clam, they bounce neutrons back into the center, starting a nuclear chain reaction. If they close completely, the core goes supercritical, releases a massive burst of radiation, and kills everyone in the room. So, naturally, you would expect Slotin to use a precise robotic arm or a remote-controlled device to handle this potential apocalypse, right? Wrong. Slotin uses a screwdriver. A standard, flathead screwdriver. Picture this scene. It is a Tuesday afternoon. Slotin is wearing blue jeans and cowboy boots. He is standing at a table, holding the top half of the beryllium sphere with his left hand. In his right hand, he is jamming the tip of that screwdriver between the 2 halves, levering them apart. He is manually controlling the gap that prevents a nuclear meltdown. The only thing stopping the demon from waking up is the friction of a hand tool you can buy at a hardware store for $2. Other scientists in the room are watching, probably sweating, probably wondering why their life insurance premiums are so high. Enrico Fermi, another genius physicist, had already warned Slotin that if he kept doing this, he would be dead within a year. Slotin didn't listen, and then the inevitable happens. The screwdriver slips. It isn't a dramatic explosion. There is no mushroom cloud. There is just a sound, a clack, as the beryllium shell drops and fully encases the plutonium core. In that fraction of a second, the room is flooded with a brilliant, intense flash of blue light. This is Cherenkov radiation, the visual scream of air molecules being ripped apart by energy. Slotin feels a wave of heat wash over his body, like opening a hot oven door. His mouth is suddenly filled with a sour, metallic taste. That is the taste of his own cells beginning to die. Slotin reacts instantly. He jerks his hand back and flips the tamper off the core, stopping the reaction. He saves the lives of everyone else in the room. But for Louis Slotin, it is already over. He looks at his colleagues, the blue light fading from his retinas, and says, calmly, "Well, that does it." He walks out of the building and vomits. He knows exactly what happened. He just absorbed a lethal dose of neutron radiation inside his body. The invisible bullets have shredded his chromosomes. His bone marrow is cooking. Over the next 9 days, Louis Slotin undergoes one of the most horrific decompositions a human being can endure. His white blood cell count drops to 0. His skin blisters and peels off in sheets. His internal organs turn to mush. He loses his mind, then slips into a coma, and finally, mercifully, dies, all because of a slip of the wrist and a flathead screwdriver. If Louis Slotin's death was a flashbang grenade, violent, bright, and immediate, then this next accident was a sniper taking a shot from 5 months away. It proves that you don't need a nuclear core to die a horrific death in the name of science. Sometimes, all you need is a single drop of liquid and a false sense of security. Fast forward to 1997. We are at Dartmouth College in New Hampshire. Meet Karen Wetterhahn. She isn't a cowboy like Slotin. She's a highly respected professor of chemistry, an expert in toxic metals, and a woman who takes safety protocols very seriously. She isn't the type to use a screwdriver to pry open a bomb. She follows the rules. On August 14th, she is working in her lab with a substance called dimethylmercury. It is a colorless, heavy liquid, mostly used as a reference standard in nuclear magnetic resonance spectroscopy. That sounds complicated, but essentially, it helps scientists identify the structure of other molecules. While transferring the liquid, a tiny drop, less than half a milliliter, falls from the tip of her pipette. It lands squarely on the back of her left hand. Now, if you were there, you wouldn't have panicked. You would have seen Karen look at her hand, see the drop sitting on her latex glove, and calmly walk over to the sink to wash it off. She was wearing the recommended protective gear. She did everything right. The drop didn't burn. It didn't smoke. It didn't smell like death. It just looked like water. She washed her hands, took off the gloves, and went home to have dinner. She probably didn't think about that drop for the rest of the year. But here is the thing about dimethylmercury that nobody fully understood at the time. It is an absolute monster of a chemical. It doesn't just touch you. It invades you. While Karen was walking to the sink, that drop was already working its magic. Tests later showed that dimethylmercury permeates latex gloves in about 15 seconds. That thin layer of rubber, which she trusted to save her life, was about as effective as a screen door on a submarine. The chemical soaked through the glove, then soaked through her skin, and entered her bloodstream before she even turned on the tap. Once inside, dimethylmercury is a super lipophilic compound. In plain English, that means it loves fat, it hunts for it, and do you know what the fattiest organ in your body is? It's your brain. Your brain is nearly 60% fat. The mercury bypassed the blood-brain barrier, nature's security guard, like it had a VIP pass. It settled into her neurons and began to slowly, methodically destroy the proteins that keep her brain functioning. The true horror of this accident is the silence. Karen felt fine. For days. For weeks. For months. She taught classes, graded papers, and celebrated holidays. The mercury was sitting in her head the whole time. A ticking time bomb waiting for the timer to hit 0. 5 months later, in January 1998. The timer went off. Karen started noticing strange things. A tingling sensation in her fingers and toes. She would be walking down a hallway and suddenly stumble, like she was drunk on a Tuesday morning. Her speech started to slur. Her handwriting became a jagged mess. At first, doctors thought it was a stomach bug, then maybe a stroke. But the symptoms got worse, fast. By the time they ran a heavy metal toxicity test, the results were impossible to believe. The normal level of mercury in human blood is roughly 1 to 5 micrograms per liter. Toxic is anything over 200. Karen Wetterhahn's blood mercury level was 4,000 micrograms per liter. Her body was so saturated with poison that her breath likely exhaled toxic fumes. There was no cure. Chelation therapy, a process to scrub metals from the blood, was attempted, but it was useless. The mercury was already bound to her brain tissue. She rapidly descended into a vegetative state. She lost her sight. She lost her hearing. She couldn't speak. She was trapped in a dark, silent prison within her own skull. She would scream and cry periodically, and her husband would have to hold her, not knowing if she was in pain or if she was just terrified of the darkness. She died in June 1998, less than a year after a single drop fell on a glove she thought was safe. It redefined laboratory safety protocols forever, proving that sometimes the things that kill you are the ones you never even feel touch you. We have covered the invisible bullets of radiation and the silent assassin of chemistry. Now, let's talk about physics, specifically the physics of pressure. You see, we humans are designed to live at exactly 1 atmosphere of pressure. It is the comfortable hug of the air around us keeping our insides on the inside. But when you go deep underwater, that hug turns into a crush. To survive, we build metal tubes and pressurize them, creating a little bubble of surface-level existence at the bottom of the ocean. But physics is a patient landlord, and if you forget to pay the rent, even for a split second, eviction is violent. Welcome to the North Sea. The date is November 5th, 1983. We are on the Byford Dolphin, a semi-submersible oil drilling rig. It's a cold, industrial beast floating on a black ocean. Deep-sea diving is a major part of the operation, and to work at those depths, divers use a technique called saturation diving. Essentially, the divers live in a pressurized chamber on the deck of the ship for weeks at a time. The air inside is compressed to match the crushing pressure of the deep sea, so they don't have to decompress every time they finish a shift. They just commute from their pressurized living room to the pressurized ocean in a pressurized diving bell. It's a high-stakes lifestyle, but as long as the seals hold, it's safe. On this morning, 4 divers, Edwin Coward, Roy Lucas, Björn Bergersen, and Truls Hellevik, are in the decompression chamber system. They have just returned from a shift. 2 dive tenders, William Crammond and Martin Saunders, are outside the chamber on the deck, helping to disconnect the diving bell from the living chamber. It is a routine procedure. They have done it 100 times. The diving bell clamps to the chamber. A trunk connects them, the divers crawl through, the doors close, and then, and this is the crucial part, you release the pressure in the trunk slowly before unclaiming the bell, but on this day, a miscommunication happens, or maybe a mechanical failure, or maybe just bad luck. Before the door to the living chamber is fully sealed, Crammond releases the clamp holding the diving bell. What happens next is known as explosive decompression. And when I say explosive, I don't mean a little pop. I mean physics throwing a temper tantrum. Inside the chamber, the pressure was 9 atmospheres. Outside, on the deck, it was 1 atmosphere. In the blink of an eye, the air inside the chamber tried to equalize with the air outside. The pressure dropped from 9 to 1 instantly. To understand this, imagine shaking a can of soda as hard as you can, and then instantly removing the entire top of the can. The gas inside expands with violent force. Now, imagine that the soda is the blood and tissues of 4 human beings. 3 of the divers inside were killed instantly. But killed is a polite word. The drop in pressure caused the nitrogen dissolved in their blood to flash into gas bubbles immediately. Their blood literally boiled in their veins. It wasn't heat that boiled them. It was physics. The autopsy reports noted that high levels of fat in their arteries had precipitated out. Looking like butter, they died before their brains could even register that something was wrong. But the fate of the 4th diver, Truls Hellevik, is the one that keeps safety inspectors awake at night. Hellevik was standing right next to the door connecting the chamber to the tunnel. When the clamp failed, the diving bell flew off, leaving a small, crescent-shaped opening where the door was jammed. That opening was about 60 centimeters long. The escaping air had to go somewhere, and it had to go fast. It took Hellevik with it. The pressure differential sucked his body toward that small, crescent-shaped crack with the force of 25 tons. I want you to look at a gap of 60 centimeters. Now look at a full-grown man. You don't need a degree in geometry to know that a man does not fit through that hole. But physics doesn't care about geometry. Helvik was extruded through the opening. The force was so violent that his body was essentially disassembled. I will spare you the most graphic medical terms, but let's just say that his bisection was at the thoracic cavity. His internal organs, including his trachea and section of his small intestine, were ejected from the chamber and found nearly 10 meters away on the rig's deck. His spine was snapped, and he was literally turned inside out. It sounds like a horror movie script written by a sadist, but the one mercy here is the speed. The human nervous system transmits pain signals at about 100 meters per second. This event happened faster than that. Truls Helvik and his colleagues were dead before they could feel pain, before they could be scared, before they even knew they were dying. One moment they were talking about breakfast, and the next, they were gone. Let's move away from the crushing depths of the ocean and head to the only place scarier than the bottom of the sea, the Soviet Union in the late 1970s. Specifically, we are going to the Institute for High Energy Physics in Protvino. It is July 13th, 1978. Meet Anatoli Bugorski. Anatoly is a researcher working with the U-70 synchrotron, which, at the time, was the largest particle accelerator in the Soviet Union. If you don't know what a particle accelerator is, imagine a giant underground donut where scientists use magnets to whip protons around at nearly the speed of light until they smash into things. It is the pinnacle of high-energy physics. It is loud, it is dangerous, and it is definitely not a place to stick your head. But on this particular day, the machine is acting up. Bugorski notices a malfunction in one of the detectors. He calls the control room and tells them to switch off the beam so he can go in and fix it. The control room agrees. Bugorski walks into the experimental hall. Now, usually, there are safety lights, big, red, flashing warnings that tell you if the invisible beam of death is currently active. But in a twist of fate that feels almost too perfectly Soviet engineering, the light bulb for the warning signal had burned out. Bugorski thinks the machine is off. It isn't. He leans over the equipment, positioning his head directly inside the channel where the beam travels, trying to get a better look at the faulty piece of hardware. In that instant, a beam of high-energy protons travels through the back of his head, passes through his brain, and exits through the side of his nose. Now, you might expect his head to explode like a watermelon at a shooting range, but high-energy physics is stranger than that. The beam is incredibly focused. Bugorski later reported that he felt absolutely no pain. What he did experience, however, was a flash of light. He described it as seeing something brighter than 1,000 suns. It wasn't light entering his eyes from the outside, it was the protons physically striking his optic nerves and the visual processing centers of his brain, triggering a signal so intense that it had no comparison in the natural world. He pulled his head out, shook it off, and finished his repairs. He didn't even tell anyone immediately. He just went home. But by the next morning, the left side of his face had swollen up like a balloon. He was rushed to a clinic in Moscow, where the doctors looked at him with the sad eyes of people who know they are looking at a dead man. Let's talk numbers. The amount of radiation absorption is measured in rads. A dose of 400 to 1,000 rads is usually fatal. Bugorski absorbed an estimated 200,000 rads as the beam entered his skull, and due to the Bragg peak effect, where particles dump more energy as they slow down. The exit wound on his nose received about 300,000 rads. The doctors waited for him to die. They watched as the skin on the back of his head and his nose peeled away, revealing the path of the beam burned straight through the bone and brain tissue. It was a clean, cauterized tunnel through his gray matter. But here is the dark miracle. Because the beam was so focused, it acted less like a bomb and more like a laser surgery gone wrong. It missed the vital centers of the brain that control heart rate and breathing. Against all known medical probability, Anatoli Bugorski survived. He didn't just survive, he completed his PhD. However, he didn't walk away unscathed. He lost hearing in his left ear, replaced by a constant, maddening internal noise. The left side of his face became completely paralyzed due to nerve destruction, and this led to the most bizarre side effect of all. As the years passed, the right side of Bugorski's face aged normally. It developed wrinkles, crow's feet, and saggy skin. But the left side, the side paralyzed by the proton beam, remained smooth. Frozen in time, it was like a twisted, accidental Botox injection from a particle accelerator. Anatoli Bugorski is still alive today, a living testament to the fact that you can literally have a hole punched through your brain by the fundamental building blocks of the universe and still show up for work on Monday. Though, I wouldn't recommend it as a skincare routine. If the previous stories were tragedies, this final one is a torture test. It is the story that defines the absolute limit of human suffering. It asks a question that no one ever wants to answer. What happens when you are technically alive, but biologically dead? Let's go to Tokaimura, Japan. September 30th, 1999. We are at the JCO nuclear fuel processing plant. It sounds high-tech, but the procedure happening inside is shockingly primitive. 3 workers, Hisashi Uchi, Masato Shinohara, and Yutaka Yokokawa, are preparing a batch of fuel. They are supposed to use a complex, automated system to mix nitric acid and uranium, but that takes too long. And when you have a deadline, safety is just a suggestion. So, they decide to speed things up. They mix the uranium in a stainless steel bucket. Yes, a bucket. Like you would use to wash your car, they stir it by hand and then pour it through a funnel into the precipitation tank. They are pouring uranium like it's pancake batter. The tank is designed to hold 4 kilograms of uranium. They pour in 16 kilograms. As Ouchi pours the final bucket, the mixture reaches critical mass. There is no explosion. There is just that familiar, terrifying blue flash. The air ionizes. The radiation alarms scream. And Hisashi Uchi, who is draped over the tank holding the funnel, absorbs a blast of neutron radiation that is roughly 17,000 times the annual permissible limit. In that millisecond, Hisashi Uchi ceases to be a biological entity and becomes a physics experiment. He arrives at the hospital looking fine. He is conscious. He is talking. His skin is a bit red, like a bad sunburn, and his hand is swollen. You might look at him and think, he's lucky, he survived. But the doctors analyzing his blood see the truth. When they look under the microscope, they don't find blood cells, they find a graveyard. The radiation has completely obliterated Ouchi's chromosomes. Think of your DNA as the blueprint for your body. It tells your cells how to divide, how to heal, and how to replace old cells with new ones. Ouchi's blueprint has been shredded. His body still exists, but it has forgotten how to be a body. He is a walking ghost. His cells are dying at a normal rate, but no new cells are being born to replace them. To prevent infection, doctors move him to a sterile room, but there is no saving him. His white blood cell count is 0. They try experimental transplants. They pump him full of blood transfusions and fluids. Because he has no skin, he loses body fluids at a massive rate, up to 20 liters a day. He is constantly thirsty, constantly bleeding, and constantly in agony. They have to wrap him in gauze and change it daily, a process that takes 3 hours and causes excruciating pain as the gauze pulls away raw flesh. At one point, Ouchi manages to write on a piece of paper, "I can't take it anymore. I am not a guinea pig." It is a plea for death, a rational, humane request. But the doctors, driven by a mix of medical duty and immense pressure from the family who isn't ready to let go, keep him alive. They put him on a ventilator. They put him in a medically induced coma. On the 59th day, his heart stops. For 49 minutes, he is clinically dead. This is the exit ramp. This is the end. But the doctors rush in. They massage his heart. They shock him. They drag him back from the void. They restart his heart, forcing his disintegrating body to endure another 24 days of hell. His muscles begin to melt away from his bones. His intestines dissolve. His eyes bleed. He is literally falling apart on a cellular level, held together only by machines and tubes. Finally, on December 21st, 1999, 83 days after the accident, his body gives up. A massive organ failure shuts him down for the last time. The doctors do not resuscitate him. Hisashi Uchi's story is the ultimate cautionary tale. It reminds us that survival isn't always the best outcome. Science allows us to split the atom and unlock the power of the stars, but it also allows us to keep a man alive long after he should have been allowed to find peace. So, the next time you complain about health and safety regulations or think a warning label is stupid, remember the Demon Core. Remember the drop of mercury. Remember the pressure of the deep sea. And remember the man who was kept alive in a bucket-induced hell. Respect the lab, or the lab will make you part of the experiment.